Hello! Are we live? Hopefully. I've got a screen now that I made 5 seconds ago. Anyway, hopefully it's okay. I'll think of something more creative soon, but something. Okay, so this is the first stream in I don't know how long, quite a while. I did the MAT today, which is their mathematics admission test for Oxford, and I've been spending a lot of time doing that and other stuff. I've just been busy. So, but we're back, and today, as you hopefully can see by the thumbnail and the title, we're going to have a look at koi. I think, judging by the fish in the logo, I think it's probably koi. Okay, so for Compactor, I've already got the some Huffman code stuff working, and I'll do some more work on that at some point. And I want to turn it into a command line tool so you can basically encode files in and out of that, which I think would be neat, and then basically making a file which could, at least for now, would just contain Huffman coding of a particular file, but then possibly when I look at other compression algorithms, I could add those different variants to a compactor file, or whatever it ends up being called, which would basically be a wrapper. I suppose it's a bit like, obviously, in a much jankier version of the kind of idea of something like an MKV, where it's a holder for other things. So the idea is that you could, any compression algorithm supported by Compactor could be put inside of this Compactor file. Anyway, that's the idea. So actually, the first thing that I wanted to show you is this. So if you remember before, on the Huffman stuff, the test took forever. It was very slow, and it timed out because Cargo gets up. Cargo test says your test shouldn't take longer than about a minute, and it kind of gives up on it, and it probably would have taken forever. And so I was looking into ways to deal with this, and I couldn't make it work on Windows, and so I put it onto a VM, and then I run it on there, and then I couldn't view it properly on there because viewing it in VS Code is very janky. But then I saw that John or somebody else is doing it in Firefox, and this is really nice interface. Anyway, here's the flame graph using flame graph. I don't think this is from Cargo flame graph. I have also used Cargo flame graph, but this one is just from piping data from perf into it, I think. Anyway, so we can see that, and if you haven't seen a flame graph before, the way that it works is that at the bottom we have all, and there's 100,000 samples. And basically what it does is it samples the program at random intervals to see, well, what's the stack trace? Where is the program spending its time, basically? And so we can see this might be a really intensive operation. Maybe we can optimize this. So we can see it's basically spinning, well, it's Cargo test, that's fine. Sorry, Huffman test, that's what we're testing. And all of this is the same. Interestingly enough, it's the random long encode decode, that's something that's taking all the time. The encode doesn't even show up. Not that I can... I can't even see the encode, so that's very quick. But the decode, that's taking all the time. And what we can see is we have traverse tree is recursive, so hence why we see them calling themselves. But if we actually go to a traverse tree, we see, well, what's using this up? It's print. So the reason it was so slow is that it was just calling print several times every iteration to print out debugging data, and that takes a long time because I/O is slow. So that's why I commented those out, and it I can show you if I go cargo test. After it compiles, it runs so quickly you can't even tell. It's, you know, it's 0.08 seconds, it says. Whereas, as I say before, this exactly the same thing here would just take forever. And I've even done it with much higher things. I think here, this is the number. I think. Oh, let me do. I think does this. That takes a little while longer, but obviously it doesn't. It would just panic if it didn't work. But you can see that only takes maybe a few seconds. So that's good, and I did another one afterwards, and you can see now there's no print anymore, and we've got in the decode doesn't take. There's a lot of these unknown things. I might be able to play around with some things to get some more information there. More unknown, but that's not so important. And in now the encoding is taking up most of the time, and I've got its sort of iterator stuff, and hash map entry stuff. So I think there might be some optimization there, but I think, you know, that's a lot better, and obviously it's many, many times faster. But one thing I found that was very annoying is that when I did manage to get it working, I mean, I got a result out of FlameGraph on Windows using not perf, dtrace, I think. And these are what I've got. So there's probably a way to fix this, and I did some other one, and this is even so. These are not functions that I've written in my code. So yeah, that's not very helpful. But as I say, I did get that working, so that's working really quickly. One of the things I will want to do at some point is I think I'm doing everything here as chars, and I think I want to switch to U8 because that would just make it easier or do it generically, because that would make it a lot easier then I could just feed in files, and if it's text, then also I don't know if chars aren't necessarily byte. Anyway, but if it's just bytes, then you should be able to do the same thing, and if it's text, you should basically have the same optimizations. So I think that would be good. Then I could, hopefully, I would be able to. Sorry, let me make this bigger. Anyway, yeah. So eventually, you'd be able to go, compactor this in this file, out this other file, and then it takes it and specify Huffman, and then it does this on it. That would also be interesting to look at some point. I think there are some methods to look if there are larger combinations. If you have a longer string that appears multiple times, that you could use that. Anyway, but I think this is a lot better for now, and I think the char to U8 thing would be basically fine to replace char to U8, because I don't think I'm really using any methods on chars. It doesn't really matter that they are. It's just what it is. Okay. So now, I think I mentioned this in the first stream, but one of the things that I found on one of the things that made me, I've known about Huffman codes for a while, but anyway, one of the videos that I inspired me to do this, mentioned the quite okay image format, or QOI, which is quite a simple, is a simple, fast compression algorithm. Doesn't use any discrete cosine transforms or any other stuff like that. It's fairly straightforward and hopefully quite easy to understand. So I'm going to go through the spec now, and then I've looked briefly through the C implementation, and though I'm not a C programmer, I know a bit about it, but not a huge amount. And I've seen bits of a video where somebody was doing a JavaScript version, which seems pretty much like a port of the C version, which is not really what I intend to do. I want to try and tackle it on my own and come up with my own version, which will probably be slower. I think that would be fun and more in the spirit of it, because this isn't a serious program. It's for the sake of, building something. And anyway, okay, so here is the spec. I just want. Don't know how you get rid of this. There we are. Okay. Okay. So hopefully this is somewhat readable. Oh, I've just realised that this is slightly cropped at the top. I know it's cropped at the bottom because it's a 16 by 10 monitor. Okay. Oh, there we go. Okay. Not that you need to see the top for this, but just in general. Anyway, sorry. So here is the quite okay image format. So it has a header which contains the magic bytes that says it's a QOI file. Basically, it has the width, the height. I need to check what the T means, but I'm pretty sure it's just an unsigned 32-bit integer. Same thing for the height. The channels is 3 or 4, and then the color space. I'll get onto the. I find some of the RGBA stuff slightly confusing because everything is based around just RGB. So I guess you keep seam alpha as the same. Anyway, get onto that. And color space. And it says that the channel doesn't change the way data chunks are encoded, but there's an RGB and an RGBA chunk, and if it's RGBA, you wouldn't use an RGB chunk, and vice versa. Anyway, but the color space I guess is purely informative. I can't see anything. So it encodes left to right, top to bottom. So on this image, it would start here. It would scan like this, come back here, scan like this, and it would look at the rows of pixels across like that, as you see it. So it sort of starts with the imaginary sort of -1 pixel as black with full alpha, and then it goes across. And so it encodes a run of previous pixels. If there's a bunch of pixels the same, it will encode that more efficiently. If there's a bunch of pixels that are same in a region, it keeps an index of previous pixels, and so it can just say, oh, go back to this pixel. It basically uses a hash map, not really, or sort of, anyway. And then also, if there's a small gradient, it can say, oh, it's just this difference from the other pixel, or it can also use what I think it calls a luma difference, which is basically have a large difference in the group, have a larger difference in the green, and then small differences between that green difference and the red difference and the blue difference. So basically saying, if the brightness has increased a bunch but the color is generally the same, then we don't need to include all of that data. We can say one channel has increased by this amount, and assuming they've all increased by similar amounts, then we just sort of store that change. So if you want to know how much the red has changed, you take the green change and then you add on the red, that red change difference, basically. We can go over that. Okay, so yeah, and it uses a 64 length array to store them, and every as far as I can tell, every new pixel that is added basically gets added to this, and it will overwrite the previous thing. And the way it's added is it uses this sort of hash function. It multiplies the red times 3, the green times 5, and the B times 7, and the alpha times 11, and takes it mod 64. And using the prime numbers means that, you know, something that's purely red can never, well, not never. I mean, if your R value was 7, then it would, but you'll get less collisions, basically. And the file is made up of data chunks, which basically represent one of these 4 things. And if you're decoding it, you need to know, well, which of these things is it? And so there's a tag at the beginning, which is either 2 or 8 bytes, which basically tells you what type of data it is. And then it ends with a bunch of zeros in them. Okay, so the base chunks, or sort of the default ones, how do you say default? More like a last resort if you can't do any optimization on it, are these ones here where you just store the full value. Now you'll notice that if you're just storing the raw values, then for red, green, and blue, 1 pixel, you need 3 bytes. But here we need 4 bytes, and the same thing for for RGBA, you'd only need 4 bytes, but here you need 5 bytes. And this is in a randomly generated image. This would probably mean that it would actually, the compressed file, the QOI file, would be larger than the raw data. But the real world isn't, you know, just random noise for the most part, at least not in a literal sense. And so most objects that we might take a picture of have colors together that are similar color. You know, you have people's skin, which tends to be the same color as itself, or objects, you know, have areas which are a similar color. And so because the other data chunks are much smaller than the 3 or 4 bytes, that we can get good compression. And obviously the amount of compression that you can get will vary significantly depending on what the image actually is. There's a scale from, you know, a run of all the same color, which you might be able to do in, depending, there's a limit to the number of runs that you can do in a single byte. But yeah, I mean, that would only take a few bytes if it was all the same color, versus random noise that would take more bytes than just storing the raw information. And there's some benchmarks and things which we can look at, and, you know, when we're going to finish the implementation, try benchmarking it both in terms of time and performance. But basically, in the real world, this does a pretty good job of decreasing the amount of size. Okay, so the index is the one that indexes into this 64 index array, and hence why it has 6 bits. Yeah, 0 to 63, and it starts with 0, 0. So that's one tag. So it's basically one of the last 60. If this pixel is the same as one of the last 64 distinct pixels, we can store it with only 1 byte. The same thing here is if we have a diff. If the this byte is only differs from the last byte by plus, between -2 and +1, then we can also store it in 1 byte. So we have 2 bits for the tag and then 2 bits for each of the differences, which is why we have 4 values, and then they've weighted that between they've offset that between -2 and 1. That is, I'm sure they did tests to determine that's better than -1 and 2. I don't know. I suspect it's somewhat arbitrary, but I don't know. That would be an interesting experiment to do. Right. Oh, and they wrap around. Okay, that seems like a minor detail that would be worth noting in the implementation. Yeah, with the bias. Okay. Yes, and the alpha value remains unchanged. Okay, and then the other one is this Luma one that I was talking about earlier, where we can have a moderately large difference in the brightness, but we can deal with a large difference in brightness as long as the color is basically the same. So as long as the ratios between the colors are similar, not really ratios, but the difference between them is similar, then we can handle a large change in color. And this one takes 2 bytes. And this uses the 10 tag, and then we have the run length encoding type thing, which basically says yes, and you have to be careful what you put in the run so it doesn't conflict with one of these. But basically, it's a run of the previous pixel. So if you have 5 copies of the same pixel, you'll have something representing that pixel here, either an RGB or RGBA chunk, or you could also have an index or a diff, whatever. And then you have a run, let's say, then you'd have a run which was 4, saying, it's just this pixel 4 more times. And that's it. So I think that's fairly simple. There's obviously various ways that you could implement this, but I think I just remembered that my camera is covering some of it. Anyway, but basically each of these so the anyway, so just each of these can be encoded as basically an enum variant. So what my idea is that if you take in raw pixel data and then you can basically parse it into a vector of these enums, and then those can then be serialized into a binary file. And I'm not sure I mentioned this, but it's also everything's byte aligned, which makes it a bit simpler. Okay, and I'm aware that may not be the most efficient way to do it, and the other implementations tend to just stick it straight into a binary buffer, but though that is probably faster, I think that sort of describing it in this way makes it easier to understand, which is really the point of it. Oh yes, and to my point earlier, if you view the flame graphs in At least in the extensions that I've tried in Visual Studio Code, they're just an image and you have no interactivity with them. Okay, so my idea is, let's add a new file, QOI.rs, and we'll want to do mod QOI. I'm never sure on what to call it. Well, this is one of the last things I was doing that you have. Anyway, that's a thing for later. So what I think would be good to do is to make that, you know. Now let me see if I actually let me oh no, is it not like doesn't like this PDF? Oh, no, it does like it. Okay. So hopefully this is okay. So we want enum. This is going to be QOI chunk. And what are the variants of this? So the first one, I suppose I can. So we have RGB. We have RGBA. RGBA. We have the index. We have the diff. We have the luma, and we have the run. Okay. So then what we probably want to do is make a struct that represents each of these. So if we do struct, so QOI RGB. Right. RGB. Okay, so for this we want, basically we want 3 U8s. So the RGB, yeah, contains 3 bytes of red, green, and blue. So we've got red, U8, green, U8, blue. Okay. So then we go up here. Let me just do expected comma. Where do you want to? Why isn't it? What am I missing? Does this have to be oh no, that's fine. You need brackets, that's it. Ah, there we are. Yeah, I don't know, because it's confusing if you... Yeah, that is confusing. So... how do you switch off the... I know you use the I know you do the macro, but I can't remember what you put instead of warn. So just like, oh no, any. So then I want to do. Ah, that's better. Can I do? Oh well. Okay, so then I want. I'll just ignore the messages for now. Okay, so then we want RGBA, and we want the alpha to also be a U8. Now, whether there should be red, green, blue, or RGB, I'm not sure. Okay, so now we want the index. Now, with the index and things like that, that's more difficult because the index is basically a U6. So I think what I'll basically do is I'll just store it as a U8, and then these are all private types, so then it will just have to be you're only allowed to put so much into them. Okay, so I guess I'll do that for now. Again, this is not trying to be the most efficient or optimal implementation, it's trying to be an implementation. Oh no, not static. Struct. This is what I want. Struct. QOI index. So All this needs is the index, which, as I say, for now I'm going to leave as a U8. Okay, now we need struct. That's going to be QOI diff, which needs dr. Again, using more memory than is strictly necessary. Yeah. Oh well. So QI diff, and then we want. I don't know why, because with the enum, it does that nice thing for you, but it doesn't do that with structs. Oh well. So we want now the luma. So this one is a bit more difficult because we have the because we have the so we have the this, which is, let's just store an U8 for now, and then we have the, I'll just call it that U8, and then U8. Okay. And then we just have the run, which is just going to be struct QOI run, and this is going to be length U8. Okay. So then what I want to do, and then here this is going to be index, this is diff, this is luma, and this is run. Okay. This isn't. This is a lot of stuff. I might put that in another file at some point. Okay. So what we would so for the, let's think about encoding first. So what are we going to call it when we turn the bytes into, because we basically want to take a raw buffer of bytes and turn that into a vector, or or whatever, or a list of some variety of these QOI chunks. So in order to do that, well, what did you call that? Would that be parsing, or okay, let's call it that for now. So parse raw, and this is going just to take a not editing it, so we could, I can never remember how to do. Anyway, so this is going to be pixels, and we want to be an array slice of view 8. And then this is going to return a vec of QOI chunks. So, and we're also probably going to want actually, we also need some other metadata. So what I was thinking might be, okay, let's yeah, so what I was thinking is what could do is basically have some struct which holds the a pixel buffer and then some other metadata like the length and the height, the width rather, the height and the width, and then that could be passed around from different things. Because I was thinking about how to turn something, let's say from a QOI to some other image format, and what would be nice if there was some way, if you basically set up all the from rules, you know, you implement the from traits and the into, so you could basically detect what the input file type was and the last one, and then you could just go this into that is what I want, and then it would do the, I don't know, if you have type A which you can go into type B which can then go into type C, or rather C implements the from type B trait and B implements the from type A trait, could you go A into C and would it do that conversion automatically? Probably wouldn't, but anyway, it's just interesting. So what we would want to do is we would basically want to have a pixel which would, for now, I'm just going to I need U8 pixel equals, and then this is just going to be let's just do 1, 2, 3. Okay. And so then let's do the things on this. So the first thing that we would want to check, I think we basically want to check them in this order, is run of the previous pixel. So what we'd want oh, I just want to comment it out. So we'd have, we'd want the previous pixel. Well, actually, we know what it needs to be. Oh wait, no. This needs to be 0,0,0,255 to start with. That's what it says in the spec. Okay. So, in order to do the run, we need to, basically one of the first things we need to do, and obviously this will be in a loop. We need to do, okay. So, this needs to be interval. so what we do, if pixel equals previous pixel, then okay, so we're going to need a run count. Let run count U8. So this we start at 0. So if the previous pixel, equals yeah, so we're probably going to need to do some figure out how to deal with that. Okay, yeah, I'll deal with that later. So if this pixel equals the previous pixel, then we want to run count plus equals 1. And that is mute. Okay. And then else if run count is greater than 0, what we want to, so basically what we want to do is we want to let right, so we want an empty accumulator, and then if the run count is greater than 0, but this pixel does not equal the previous pixel, that means we've broken the run. So what we want to do is we want to set the run count equal to 0, and then we want to push onto there a QOI. No, this needs to be QOI chunk QOI run with length. No, these need to get this way around. Length run count. Expected function. Oh, that's why. So we need this as well. I don't know why it's saying value assigned to run count is never read. Maybe it's because there's not in a loop, so at the moment it can't reach either of those, but okay. Yeah, okay, that's fine. And else, that's fine. We just, there's no other thing. We just move on to the next thing. But also if we're in here, then we'd want to continue. But since we're not in a loop yet, we don't want to. But yes, we would want to do that. Okay. So the next thing we want to check so now we need this index. So let's do fn index hash, and this takes pixel. Again, decide on how to do this. Type but it takes that, and it is going to return a U8. And so all this, I suppose, you can just, it's just going to be this. So it's going to be .0, because that's going to be red, green, blue, times pixel dot 1. Oh wait, no, this needs to be times 3 plus times 4 plus, let me, right, so now we want 2, 5, 7, 3 and 11. And then this is going to be mod 64. Excellent. So here what we, so then we want to do let mute I don't know what would you call this? I'll just call it index array. So this is going to be an array of colors of length 64. And we want this equal to 0, 64. Can you do that? Excellent. But we want the initial pixel, which is 000255. That needs to already be in there. And so 255 times 11 mod 64 is 53. So we know that we want index array 53 equals this thing here. Okay. So then at this point we want to do let index equal to index hash of pixel, and then we want to do index array at index equals pixel. I wonder how you implement index, because I mean, there's not really I guess I'll just have to do this. This is just easier, and then here I'll do as usize. Oh no, because yeah, I guess that's fine. Okay, so then we do that. So actually, I suppose what we would want to do first is we would want to check if it's already in there. Right, so before we do that, we'd want to say if index array index equals pixel, then what we would want to do is, well, that's it, we're done. We just do just push to the accumulator. Let me just copy this. I don't know why it's not auto completing that. So it's going to be a chunk, and this time instead of a run, it's going to be index, and inside the index, it's going to be a QOI index with index is going to be that. Could I go as U8? Does that work? Good, and then again, this would be a continue point here. Okay. So then we'd want to do a difference of the previous pixel. So because the normal diff here takes only 1 byte and the Luma takes 2, we want to preference this one. So what we would, yeah. So what I might do, I think we've outlined, well, the sort of the first part, outlined the sort of idea, the way that it works, and I suppose what it is. So I'll think about how to handle the color and the pixel and the. I mean, it's harder because it could be 3 or 4. But I suppose what we could do is just treat everything as RGBA, but then the only difference is if it's 3 channels, then you add an RGB chunk, and if it's 4, you add an RGBA chunk. So I might just do that. Anyhow, I think it's probably good for today. I'm just grateful I've got that exam over with, and hopefully I'll be able to stream more regularly now, and I'll be able to get this implementation done, because I find it very very clever. I mean, I don't think it would take very much more longer to do this. Then I just need to turn the chunks into bits, and then need to do the reverse, and then once I've got the chunks, then I need to turn that into raw pixel data, which should be doable. Thank you very much. Thank you very much. I hope you found that interesting or enjoyed. Comment if there's anything you'd like to see me do. Subscribe for the next one, and